thing.
Okay.
What went through my brain was, what happens if this is broken for like 2 weeks? How on earth am I going to do this class? And that was not a pleasant thought. So, Kelsey, oh good, thank goodness you blinked there. You looked like you were stationary. Okay, so, give my brain a second to settle down. Right, so what I'm going to do today, my first goal is we're going to look at finding limits of vertical asymptotes. That's kind of where we left off last time. We're going to touch on how you can do it if you've got a graph in front of you, or create a graph for that matter. How you can do it using tables of values, and we're actually going to show you how you can find limits where there's vertical asymptotes involved using what I'm calling logic, which is basically just using mathematical common sense, right? And we'll get that done, even although we've had a little hiccup with time, we'll get that done before the end of today. And that means I can start section 2.3 as well. And we should finish 2.3 tomorrow. So that's kind of my goal, my big goal. So let's look at what I mean by finding it graphically. There are two versions of that. The first one would be something like this, where you would have, try to do one here, goes like that, just like that. Just like that. Right, suppose you had a function, a graph of a function that looked like this, and we'll make this x equals 3, and I'll make this x equals -1. If you were being asked to find left limits, right limits, or overall limits, you can actually just look at the picture and you can tell, hopefully. So if I was being asked to find that guy, we'll assume this function is f of x. That is called a right limit, okay? You're coming in from the right-hand side. Well, as you come along, right, as you choose values of x here, can you see that you're going to zoom upwards to positive infinity? If I asked you to find this fella, would you also agree that this is called a left limit? And that's you coming in towards 3 from the left-hand side. And as you do, isn't the function zooming upwards, isn't its y coordinate also plus infinity? And so the overall limit in this particular one exists, and it's positive infinity. On the other hand, if you look over here at x at -1, there is a vertical asymptote, but isn't it one of those vertical asymptotes where it curves up to infinity on one side and goes downwards to negative infinity on the other? And if I look at that, I hope you would agree with me that the overall limit, right, does not exist. Would you agree? But isn't the left limit plus infinity and the right limit negative infinity? So I think it's a very simple question. If someone gives you a nice picture, right, and a couple of the homework questions, isn't that what they do? You just get a nice picture and you can write down plus infinity, you just write infinity. Negative infinity, you stick a negative in front of it, and does not exist. I don't think you put the decimals here. I think you just say DNE in WebAssign.
So what you wrote there
is
what you wrote is the -1 is DNE, but you meant just, oh, that's not, that is -1, but it's not -1 negative.
Yes.
Oh, okay.
Yes. Yeah, that's an overall limit. That would be the left limit at -1. That's how you would write it. There are a lot of negatives in that one, isn't there? And that would be, even weirder looking, that would be the notation for a right limit. And in this question, that's negative infinity. And in this one, it's positive infinity. Are we comfortable with, if you get a picture, you can tell what's happening at vertical asymptotes? Okay, so there is another version of that graphing I want to show you. You know something's going to go wrong here. I'm about to hopefully, let's put it that way, I'm about to figure out, I didn't mean that, I knew I would do that. A piece of software that I've got that should help me. I just want to find the question. And so a very weird looking question. Can I find it? Darn if I can find it. Okay, I'll just make one up. Suppose I was being asked to find left limit at 1, the right limit at 1, and the overall limit at 1. Is it pretty obvious in this function that x equals 1 is where the vertical asymptote is? And that's why they're asking these questions and not any other value. Now, I don't have a graph, but I'm still going to do it graphically. And the way I'm going to do that is I just want to show you another way of doing it. Here's the dangerous part. I'm kind of worried every time I change windows. Right. What I got here is a TI-84 emulator. So you go y equals, put brackets around the top, which is 2x add 1. Divided by x minus 1 squared. And then you just pick a window. Since I'm interested in 1, I'll probably pick a window from 0 to 2. And then I'll do zoom to fit, which is zoom 0. So if you're used to using the TI-84, there. It's maybe not the prettiest picture in the world, but isn't there enough there to see what the heck's going on? Isn't the left limit plus infinity? By the way, right there is where x equals 1 is. Right. So would you agree the left limit is plus infinity, the right limit is plus infinity, and the overall limit is infinity? So you can use your TI-84 calculator, and that works fine, and I have no problems with that. It's kind of quick, but there is other ways in which we can do it. So I want to show you if I can open up again the right window. I'm not sure what window I'm opening right now. And I'm going to use Desmos. And we'll show you that Desmos can be used to graph things as well. Okay, so I'm going to go out. I'm going to go, oh, I've got a chart. Should I be looking at that? Whatever that's about. Here we go. Now in Desmos, you can type in your graph as y equals. If you go brackets 2x plus 1, hit the divide symbol, which is in the bottom right-hand corner where the question mark is. And then you can go x take away 1, close brackets. If I use this little guy down here, I can get the square. And it's a little bit more professional than your TI-84. Would you agree Desmos has color in it and it's more manipulatable? Yeah, you can manipulate it more. See, if I zoom out a bit, does that emphasize the vertical asymptote a lot more? And if I zoom in and scroll around a bit, can you see I can focus quite easily on whatever I think is important? So if you have a question and it involves a function and you're being asked to find the limit as x tends to a number, and you know that there's a vertical asymptote here, wouldn't this technique be quite helpful for plus and minus infinities and so I think that's all I want to say about vertical asymptotes in graphing. We feel good about those questions. Yes, Teresa.
Okay, sorry. So are we assuming by looking at this that at 1, these two lines all the way to infinity will never cross 1?
Correct. They never shall.
They'll never.
The reason why they can never meet, or infinity is not like a destination, a point where you can meet. Infinity goes on forever. The reason I can tell that, if I plug in 1 here, don't I get that dreaded number divided by 0 problem?
Right.
And that's undefined, and it's undefined because there is no point in the universe that's equal to 5 over 0. Right? It's it goes on forever. So no, they never meet. I could zoom this till the poor thing broke, and it might look like
they do. So I just
when you zoom back in, do you see there's always going to be a tiny little gap?
Yeah.
Right.
It just seems like at some point out there in infinity that those suckers are going to reach the same point to me, but
yeah,
we'll just assume they don't.
Yeah, they don't.
Mathematically, they can't.
Just don't. They just won't. I think that's all I want to say about graphing then. Have we got, we move on now to table of values. So how would table of values questions look? Well, let's pick, actually, no, I don't want that one because it's all plus infinity. So let's do somewhere a little bit more in it. Right, let's suppose I wanted to find out a little bit about this function here. I'll make it x minus 2 cubed. That's more interesting. There we go. And you're going to be asked to evaluate this function at various points near to 2. So you're going to have x and f of x.
Sorry, I don't know. I can't see your paper. I don't know.
Oh, I forgot to change over. Thank you for telling me. There we go.
Thank you.
So we've got this guy over this guy, and essentially table of values. I'm going to look at one so I can do a sort of a pseudo version of that same kind of question. Nah, I didn't have one. Okay. You might have 1.9, 1.99, 1.3 lots of 9, 2.001, 2.01, and 2.1. So what you do is you evaluate this function at these key points. And do you notice they're not random? Do you notice I'm starting at a number? If I draw a little x-axis here, there's the magic 2 that we don't know. We know a vertical asymptote's happening, but we really don't know yet what the situations look like. But can you see I'm doing like a 1.9 and then a 1.99 and then that one and then that one. And then on the other side, it's the same kind of thing, right? Isn't there a kind of starting outside and working your way in, right? Starting reasonably far away from 2, but then getting closer and closer to 2. And what that should allow us to do is to find left limits, right limits, and then from those two things, what the overall limit is. So we're going to use a table of values to figure out who the left limit is. We're going to do a table of values to find out who the right limit is. And once we know that, we can then decide what the overall limit is. And put this on calculator. And I'm going to show you table of values again. Okay, here's my calculator. Boom. Clear that guy out of the way. Go here, clear that guy out of the way. Right, the function we're doing is 2x add 5 on the top. Divided by x minus 2 cubed. Right, so you put into Y1 whatever it is you're interested in getting the table of values for. You see this little guy here, the second button, it says table setup. So blue button, table setup. Just change this one here, the one that says independent. Scroll down, go over to there and hit enter. We're now in ask mode. Right, that's what you do. You then go over to the end here and it says table and you go blue button, table. And now I can type in those numbers. 1.9, 1.99, 1.39, then what, 2.001, 2.01, and lastly 2.1. Okay, and since I've got these guys in front of me, the first answer is negative. Can you hear me?
Yes.
Yes. It just cut out for a second.
Okay, I'm having a weird day today. Can you hear me now?
Yes.
Could you hear me when I said, could you hear me? Okay, right. My earphones went and told me that I'd been disconnected, which I hadn't. Go figure. Okay, so we got this number here. Now, what on earth does negative 9e6 mean? I'm writing it down, then I'll go to the paper. And then it's negative 9e9. And then it's 9e9. It's 9.02 E6. And then finally, it looks like it's 90,200. Okay. This table of values is meant to tell me what the vertical asymptote is looking like. And TI-84 isn't always going to tell you things the way you think it's going to tell you. So, see this number, negative 9e6? It's actually negative 9 times 10 to the power of 6, which is negative 9 million to normal human beings. Would you agree that is massively big and negative? Would you agree that negative 9e to the 9 is negative 9,000 million? Kind of like the American debt, right? That kind of number. So what does this tell me? Well, if you start at 1.9 and you evaluate the function and you get closer and closer to 2, doesn't the number just get really, really, really big and negative? And really big and negative means it's negative infinity. And these guys here are like 9,000 million, 9.02 million, and just 9,200. Can you see as you approach 2 coming from the right hand side, going this way, isn't the answer getting really big, but really big and positive? And that makes this one, it does not exist. So when you do a table of values and there's a vertical asymptote involved, these numbers will look strange. The calculator is almost guaranteed to, at least in a couple of the places, become scientific, right? It's going to go E10, E9, E22 on you. And if there's a negative there, that means it's negative infinity, essentially. And if it's positive, it means it's positive infinity. Are we good with table of values? Right. So I could pick any function in the universe and focus on just one place, in this case 2, and I should be able to get some numbers here that will tell me whether it's plus or minus infinity. In a way, it's kind of easier to do this because isn't the answers for all vertical asymptotes plus or minus infinity, or it doesn't exist? when you do numbers, don't you have to do a little bit of guesstimating? 2.4998 is probably 2.5. You know, you have to do that little round off thing. But with the infinity ones, the vertical asymptote ones, that's not really necessary. I mean, if I wanted to graph this thing, I bet you it would look like that. You can see the negative on one side and positive on the other. I'd be pretty sure it looked like that. And that's what I mean by table of values. Any questions? Are we good? Okay. Third method, using logic. Okay. What's that like? Well, before I show you me using logic, let me explain some truths, some truisms. Do you know if you take 7 and you divide it by a very small positive number, the answer you get is a very big positive number. Does that seem logical? Does that seem a reasonable assumption? That if you take the number 7, and I could do it in my calculator here, right? If you take the number 7 and you divide it by a really, oops, clear that out of the way. If I take the number 7 and you divide it by a really small number, you know, like that guy, don't you get a really big answer? Agree? Now, that is an example of what we're going to do today. We're going to do logic based on what is a reasonable assumption. What do you think -6 over a very small positive number would get you?
A very small number.
You think? So -6 divided by a very small positive number. Right, like that. What do you think that might get you as an answer?
Very big negative number.
That's what I would assume. Let's see if I'm right. Yeah, that's a pretty big negative number, isn't it? Now, why is that happening? When you divide by small things, don't you get big answers? And when you divide things by big numbers, don't you get very small answers? Don't they kind of work in opposites, right? If you multiply something by a big number, don't you get a big answer? And if you multiply something by a very small number, don't you typically get a small answer? So multiplication works in the direction of the thing you're multiplying by. But doesn't division kind of work the opposite of that? Dividing by a very small number gets you big answers. Dividing by very big numbers gets you small answers. Now that's the logic I want us to keep in mind, because that's the thing that's going to help us do these questions in a few minutes. Now, there are some combinations I haven't done yet. What would a number like -7 divided by a very small negative number get me?
A very big positive number.
I agree. If we forget about the signs for a minute, if you divide by a very small number, don't you get numerically a very big answer? But if the top number is negative and the bottom number is negative, because they still keep their sign, right? Positive things are still positive, negative things are still negative. Don't two negative things divided always generate positive answers? Does the logic behind that seem reasonable? Right? A negative number divided by a very small negative number gives you a very big positive. And the other permutation that I haven't done here is, say, a negative number with a very small positive number. So what would -7? Oh, I have done that one. What one have I not done? Oh. There's the combination I haven't done. A positive number divided by a very small negative number. And what would that combination do? Positive number divided by a very small negative number.
Very big negative number.
Have you noticed that every single one of these situations generates a big number? Sometimes a big positive number, sometimes a big negative number, but always very big. Now, I want you to think the word big and think infinity. So what you're going to get is, instead of a very big positive number, think of what's the biggest positive number you can think of. How about positive infinity? Or negative infinity? So let's do a logic question now and see how that would be implemented. Suppose you were being asked to find the limit as x tends to the left, so a left limit of 2 of 3x plus 1 over x minus 2 squared, right? And you know that there's a vertical asymptote here. So you know the answer is plus infinity, minus infinity, right? Essentially, because it's a left or right limit, you don't need to worry about it does not exist right now. So according to the logic, I am going to put in a number that is very close to 2, right? But just a little bit shy of it, like a 1.999 kind of thing, right? Let's see what that looks like. I know it's not quite 2, but isn't it near enough 2 not to matter? So 3 times 2 plus 1 is about 7. Would you agree? Or very, very close to 7. It won't matter if it's a little bit over, a little bit under. It's pretty close to 7. Now, on the other hand, this is where it gets a little bit messier. If the x value I'm picking is a 2 minus, doesn't that mean it's a 1.999 kind of guy? Won't x take away 2 be a 1.999 kind of guy? Take away 2. Now, won't that be a version, a very small number? But will it be a very small positive number or a very small negative number? Right. What will you get if you plug one? Negative. Now, can I just put in a little negative 0? All I'm meaning there is negative small. Maybe I should just call it negative small. That's probably better. Yeah. Oh, but then you square it. What happens if you take a very small negative number and you square it? Don't you get an even smaller positive number? Would you agree a very tiny negative number times another very tiny negative number gives you an even tinier positive number? Okay, what's 7 over a very small positive number going to get us?
Very big positive.
And don't we call very big positive infinity?
Yeah.
Right, and so that's the logic that I'm using. Now, I'm probably making a meal of that, but you get the gist of how the logic is working. It's not the kind of thing you can write down in a very coherent mathematical way, right? It's a kind of, you do it in your head mostly, right? So kind of you just think it through. Right, let's go the other side and see what would happen then. If I did a 2 plus to this, wouldn't the top be pretty close to 7? That's what the squiggly marks looks like. Okay, if you pick a number that's coming in from the right-hand side, won't it be like 2.001? So won't that be positive? And when you square it, it is positive. And isn't 7 over a very small positive thing plus infinity as well? Skip some lines there. That's positive, very tiny and positive. You square it, it's even more tiny and positive. I'm just putting positive, okay, positive and tiny, right? Whatever. And isn't 7 over a very tiny positive number, positive infinity? And that makes the overall limit in this case it makes it infinity. Okay, I'm going to give you one to try.
I have a question.
Yes.
All right, so when you go X, when you do the limit for the -2 and you're coming from the left, I feel like it needs to be the 2.001, like negative 2.0.
Yeah, it should be, but this is positive 2.
Oh, this is
isn't
positive
negative 2.
2.
This is 2 coming. This is positive 2.
Oh, that's
If
right.
it had been negative 2 minus, that would have been
I see. I see. Oh, I'm getting confused by looking at that little negative sign. It's throwing me off. Oh no.
Yeah, that little negative sign doesn't mean negative.
Yeah.
That little negative sign means you're just a little bit smaller than 2.
Okay.
Right, here's your guy. No pressure, because you can do these in your head, hopefully. You got 1 minute. Find those guys. Okay, here goes. You do this one. 2x plus 1, I don't know, I seem to like 7 today. 7. The top's just a number, so it can be 27. It won't change the result as long as it's positive. In this case, this is a left limit. So what we're picking is what, 2.99 kind of guy? So won't that bottom be negative? Very small and negative? And that situation generates negative infinity, doesn't it? Now, if we do a 3 plus, won't that be positive? So what do you get? 7 over a very small positive, and that gives me plus infinity. So if I'd asked you for the overall limit, wouldn't the answer be does not exist? Right? The overall limit does not exist. And that was finished. Section 2.2. Any questions before we move on to finding limits using algebra? Good. Okay, here we go. Well, we'll get a start to this. I'm not sure how much more we'll get than that. In section 2.3, you're going to be looking at how do you find limits, not using graphing, not using tables, not using logic, but purely through algebraic means. And we're going to use what are called the laws, limit laws. They're basic algebra laws. And the techniques for finding limits pretty much boil into 4 major categories. And the first technique is called the evaluation method. And it's very simple and very often the one we forget to do. And that actually should be the first method you should try. And if that fails, then you would then use one of the three methods that are left. This method is factor and cancel. That's very common technique that you'll use. This one is called the conjugate method. You should only use this algebra technique if there's a square root in the question, right? So if it's the square root of x plus 1 minus 1 over x minus 1, right? Some square root somewhere. You're probably going to use this technique called the conjugate. That's rarer than the factor and cancel. And then the last one is really a catch-all, which is just use algebra to simplify the damn thing. And hopefully when you simplify it, it will then turn into one of these guys here. So let's show you the first method, which is called evaluation. And it should be, as I said, the first method that you look. So let's suppose I'm being asked to find the limit as x tends to 3. So it's the overall limit. And it's x squared plus 7. Oh, let's make a fraction. X squared plus 7 over x plus 1. Well, the laws of limits says if you can evaluate this expression at 3, then that's what the limit will be. So it's almost silly in a way. But 9 add 7 is 16. 3 add 1 is 4. There's your answer. It's almost like I'm not really doing anything clever, which I'm not really. I mean, if you want to find the limit of a function, if you can get the answer, shouldn't that be the limit? That's again, essentially what the law is saying. And you should check it. So what's going to happen then is that you're going to try and evaluate it. And the dreaded 0 over 0 is going to happen. Remember the indeterminate form problem that keeps coming back and biting us, right? So you try it and it don't work. So you then have to move on to one of these three techniques. So let me show you an example, and we'll do lots more of these, but at least I'll give you a taste of it. Let's do the example of the limit as x tends to 2 of x squared minus, well, I need a 2 here, don't I? There's 4. What do I need? 4. There we go. Let's suppose I want to find the overall limit of that fraction. The method that we're going to use is called factor and cancel. And I like that name because it kind of tells you what we're going to do. We're going to factor it and hopefully get some cancelling. Right now, if I try to do the evaluation method, can you trust me that the top ends up being 0 and the bottom ends up being 0? Right? Can you just, I've done it in my head, it ain't happening. So we move on. And if the expression looks like it's factorable, if there is such a word, then you should do it. This guy is x take away 2, x take away 5. And this guy is x take away 2, x plus 2. So if you thought you'd seen the last day factoring, you're wrong. And when you get to Calc 4, those of you who do Calc 4, and you think, I'll not need to worry about factoring then, you are wrong. You will do factoring for the rest of your math career It never goes away. Just pretty much nothing goes away. Now, after you factor it, if you're really good and lucky, won't there be some cancel going on? X minus 2 cancels with x minus 2, which is allowed according to the laws of limits, that you are allowed to cancel the same term top and bottom. And so I've now got this guy, but this guy is doable. And the answer is -3/4. And that is the exact value for the limit, right? It's not an approximation. It's the exact value. Do you like factor and cancel? I guess if you like factoring, the answer is probably yes. Evaluate, I kind of like, because it doesn't involve a lot of brain work. So far, so good. Okay, I know I'm pushing my time and your time is valuable, but I do want to show you the third one once. And we will do a lot of practice tomorrow on these, so don't think that I'm going to just show you one and move on. If you ever see a square root, you're going to be using the conjugate method. So let me show you an example of that happening. Can you trust me? If you evaluate this, you get the 0/0, right? So the evaluation method works. Would you also say there's no way in the world that's ever going to factor, because you don't factor things that look like that, right? So you kind of know it's not the first two methods, and you're running short of methods, aren't you? Because there's only 2 more to go, and this is a conjugate method. So what on earth do you do? You multiply this fraction by a special version of 1. If you multiply anything by 1, don't you not change what it's worth? You might change the way it looks. Now, I'm not talking about 1/1, because that wouldn't be very helpful, or 2/2, or x/x. The special version of 1 that you use is called the conjugate. That's where it gets its name from. See the guy that's got the square root, this guy here? The special version of 1 I'm going to use is the same 2 guys, but with a plus instead of a subtract. Would you agree that that ugly thing there is 1? Right? It's the same thing top and bottom. It is 1. What this is going to do is it's going to fundamentally change the original fraction into something that we can work with. I'm not going to do anything at all to the bottom except write them like that. I am, however, going to multiply these 2 weird looking guys together. Do you recognize FOIL? Yet another thing that's never going to go away in your math life. So FOIL, let's see it. There's the F of FOIL. What does the square root of x plus 1 times the square root of x plus 1 get you?
X plus 1.
Yeah. Now, if you do the O, which is basically this guy times this guy, can you trust me, you get 2 lots of the square root of x plus 1. And then if you do the inside, you get -2 lots of the square root of x plus 1. And then if you do the L, -2 times +2, you get -4. And something quite magical has now happened. It's just kind of pretty. What happens to these 2 guys?
Cancel.
Yeah. And that's not a fluke. They always cancel. So essentially what you've done here is you've figured out an algebraic way of rewriting the original fraction without having those square roots that are causing the trouble. Because, can I count? Yeah. Yeah, so what do I have left? I have an x plus 1 and a takeaway 4. Which of course gets me x minus 3, put a little bracket around it, over x minus 3, the square root of x plus 1 add 2. Not only did the square roots disappear, something else magical has happened. Can you see a cancel? Now, in this case, it happens to be x minus 3, x minus 3. Sometimes you've got to be careful. Sometimes it's 2 lots of x minus 3, right? You have to pull out a common factor of 2 or something. But it's still going to be that basic pattern. Remember to leave a 1 behind. And so the answer is the limit as x tends to 3 of 1 over that guy. So that was my original problem. This is the new one. Well, you might just say you've swapped one ugly square root for a slightly less ugly square root. No, I've done more than that. Can't I plug in 3 now? 3 add 1 gets you 4. Square root of 4 is 2. 2 add 2 is 4. Can you see I can now evaluate the answer? It's a quarter. Now, isn't that kind of cool, clever, sneaky math? Whoever it was, I do not know, maybe nobody knows now, it probably was done a long time ago, but whoever took that problem and figured out that this conjugate trick was going to be of help deserves some brownie points, don't they? Because I'm looking at that and I know the method, so it's a bit hard to imagine, but I could imagine the first person to look at that problem would probably just give up. Right? I can't plug the number in. I got 0 over 0. I can't factor it. I don't know what else to do with it, right? There's not really a lot you could do to it until that guy figured that out. By the way, guy can mean girl or man. Guy to me is generic for both of you, right? Or whatever combinations there are. Are we cool with that? Say hi, everybody.